I posted that in the chat.
Okay. Yeah. So let me start sharing screen. Single object. Okay. Yeah. So we were at weak isolation levels, right? So yeah. So I was just reiterating that basically when multiple processes are concurrently writing data, the problem with strong isolation levels is that they are very expensive, because if each of the process, if each of the thread is if they take locks and they try to provide strong isolation levels, then our application will become very slow, right? So a lot of the databases these days, they try to follow weak isolation levels so that their overall data systems are highly performant and highly available, right? So last time we discussed this read committed isolation level, where we said no dirty reads and no dirty writes, right? So so the problem with this weak isolation level, which was discussed last time, is that if a long running process is trying to access the data, uh, so yeah, we're here. So if a long running process is trying to access the data, uh, it might see like some snapshot of the data is different during the initial phase, and the data might have changed when it is trying to read some other data entity at some later point of time. And so it will not see that consistent snapshot of the data, which might be a problem in some cases. And in the book, there was a good example of what they have shown. I do. So, Vivek, can I can I also show the like? Can I show the book? I have access to book online. Can I show it here? Would it be fine, or it will have some legal issues? But let me quickly bring that image.
Yeah, he's saying that we cannot.
We cannot. Okay. So
Yeah,
I'll just
he sent a message in the chat.
okay. So let me just pull the screenshot then. Okay, yeah. So so this was a very good example. So uh, let's say here, so this user Alice, he has two bank accounts, right? And so both of these bank accounts have $500 balance, right? So now he has initiated a transfer from his one of the bank accounts to another bank account of $100, right? So so this transfer process is going in the background, and this is Alice. He's viewing the state of his accounts, right? So initially he saw that his account one has $500 balance, right? Now let's say the transfer process got initiated, right? And uh, it has uh, so here from this bank account, it has added $100 here, and it has removed $100 from this bank account, right? So now he will see that in this bank account, he now has $400. And initially he saw that in this bank account, he has $500. So overall, he will see that his money is 500 plus 400, which is $900. So he might have an illusion that he has lost $100. Although once this overall transaction got completed, so basically this was this time frame was when we had the transaction, right? This is the time frame, when a transaction was going on. So his one view was before the transaction and one view was after the transaction, right? Now, if he would have accessed this account one after the transaction has completed, he would have seen that now this bank account has 600, so everything is fine. But for a moment, he will feel that because he read account one before the transaction and account two after the transaction, so he will feel this $100 has been lost, right? So this is the problem. So you can consider this, that this was a long running read process where the read started at this time and it ended at this time. And if this long running read process was part of your day-to-day job, which you have to do, then you might, if the data has changed in the middle, right? So this was a long running read process and data has changed in the middle. In the middle, the data has changed. Then you will not get the correct snapshot of data, which will be a problem, right? So this is the problem which happens in backup systems, or if you're running long batch processing job, batch analytics job, which are reading large amount of data, right? And it takes a considerable amount of time to read that data. So to avoid this problem, what is done is that you take a snapshot, you take a consistent snapshot of the data. And so what that means is that when you are reading your data system, you're reading from the snapshot. So in the snapshot, nothing is going to change, and the reads and writes will be applied on the snapshot as a different process, as a different version. But in the snapshot, you will be seeing that consistent view of your data, right? Okay, so now, so the thing is now, how do we implement this kind of snapshot isolation system, right? Okay, so
Abhishek,
yeah.
I have one question.
Mm-hmm.
So like this problem would be before snapshot isolation, right?
If we don't have snapshot isolation, if we are reading some piece of data which is changing, so we started the read here, we ended a read here, right? This was my start point of the read, this was my end point of the read, and my data has changed in the meanwhile.
Yeah.
So,
yeah. So my question is like these reads will be also a transaction, right? So if you see from the DB point of view, first, and the LS request will be also a transaction in DB, and the transfer request is also a transaction. So how multiple writes and reads are overlapping here?
So overlapping in this, like, what do you mean by overlapping? What exactly do?
Overlapping means like Alice started the read and we returned 500, but at the same time we started a write transaction which will update from 500 to 600, right, to account one. So can, like, if we follow no dirty read, no dirty write, like we will have one transaction, like if I'm not wrong, uh, like first transaction to be committed and then we can start another transaction, right?
Yeah, right. So this is what, so this is what he's saying, that so if you see in this whole system, it follows all the principles of read committed isolation. There is no dirty read, there is no dirty write, right? So when he's reading the balance at this point, so he's not reading anything which is uncommitted. 500 was committed, right? So all the reads are not dirty read. Similarly, when we are writing, we are not overwriting or we are not doing any concurrent writes. We are just adding this $600 to this account one, and we are subtracting $100, and they happened separately at different times. So there was like no dirty writes. So this is what we are saying, that it has followed all the principle of first isolation level, which is read committed isolation levels, but still in some scenarios this kind of isolation level might create problems.
Okay, so can we conclude like the first read committed isolation levels handles read, write, but not read, write or write, read combination?
No, so here in this scenario, what's happening? So transaction one so the Alice start the transaction first, and then there's another transaction start after that. But the second transaction commit before the first transaction actually, Alice actually get the balance from the second account. So now it will read that because that the second transaction already committed that. Do you follow it?
So yeah, that's what I was trying to say. Like this read and
yeah. So here you see that I mean the second transaction already committed, and now the first transaction actually reading here. So because this is already committed, so now it can read it.
yes. But I think the problem happens because Alice first write 500, and then there was a change. Like while the read request was returned, there was another write. So I was thinking like this read and write, they're kind of overlapping.
No, these are the separate transactions. So even though it's the second transaction right here, so the first transaction will not see until here.
So Praveen, but like this one entire read process here is a transaction for me, that I'm looking, I want to look at what is the balance of my bank accounts, right? So this entire thing is a transaction, and I think this is what she's saying, that so now when this transaction was getting completed, the entire read process, in the middle someone has written. So someone has written in the middle of when my read, actually the entire read transaction got completed, right?
Yeah, so when the second request for your transaction start here, the first transaction start here and commit here, and the second transaction is starting here and committing here.
Committing here, right?
So this diagram shows that how read commit, what is the problem with the read commit. So when Alice read start the transaction and it read the committed value, which is 500. So far so good. And second transaction also read the value, which is 500, which is also good, and it's also update that value, but not commit. So now if let's say if Alice read again here from the same account, she'll also again get the 500 because the value is not committed yet. And now when she this second transaction, this guy update the value to subtract the value from the second account and then commit that. So now after that point, if they make any read request, so because now it's a read commit transaction, so it can read the committed value. So now committed value is that's new value, subtracted value. So that's why it's actually read 400. So that is the issue with the read commit transaction.
So what's the issue? So it has read the value which is committed, right? So so according to the first isolation level, it's not a problem, right?
Yes, for read commit, that so the value, so in she saw that I mean the first account has 500 and second has 400. And though she was having total 1000 in both the account, but now she sees that okay, there is only 900. Where are my 100?
$100, yeah.
So that is the problem with the read commit. So that's why the new transaction level, that snapshot actually resolve that problem.
Yeah. Did you understand it? I think Neha.
Yeah. So what I was trying to conclude, like I got this like this problem I got, but what I was trying to conclude that read committed level solves the problem of if there is a read and read, or right, like we read something, once it's committed then we read, right?
Yeah.
Or write and write, like no dirty write. So like we are writing, first committing and then writing on the same object.
Right.
But here the problem is we are reading and at the same time we are writing something on the same account. So that's why the problem is happening. So
I think I think you are right that this problem is happening because you are writing something while you were reading, right? So
yes,
yeah.
yes.
Yeah.
So
Mhm.
yeah, what I was trying to conclude that read committed level solves the problem of read write, but read write
Not
or write read combination it don't solve. That's
it
why
don't. Yeah. Makes sense. Yeah. Agree. Okay. So yeah. So now okay. So now let's see how we can implement this kind of a system, read snapshot kind of system, right? So one thing.
Abhishek?
Yeah.
Yeah, I got a doubt in this one. So,
Hmm.
when you are writing a particular transaction in a database, I mean, if you're writing the code or something, you generally write it like begin a set of SQL statements, then a commit.
Mhm.
Uh, I'm not sure how. I mean, if you're committing at the end of I mean, the transaction is. I mean, from my understanding, I may be wrong, but the statements which are between begin and commit are treated as a transaction.
Right. Yeah.
Yeah. So if these are in between begin and commit, there is no reading of transactions that are occurring simultaneously, right?
Yeah. So there are two points here. So one thing you are saying, so this when write will happen, this will is the begin of the transaction and this is the end of the transaction. So nothing, whatever you are writing at this point, it will atomically be written. Like no other process will be modifying it. The other thing is that my question is, does that happen for read also? That for read also, do you specify the start and end of the transaction? Do you
So,
know?
I mean, as far as I know, everything in between a begin and a commit is considered as a transaction. You can
Mhm.
have reads as well as writes as well.
As well. Okay. So okay, yeah. So I got your point. So I think what we are saying is that so when we put something between read and write and we expect it to be a transaction, we have left it up to the database, right? That database will be following the principles of a transaction. So what they're trying to explain is that uh, it depends like how your database has implemented those isolation levels. If your database has implemented read committed isolation level, then it will not give you a consistent snapshot if your reads are happening uh, between the begin and end of the transaction. So, I mean, it depends on the database how strong isolation levels it is providing. But if you are using some kind of a database which provides read committed isolation level, then although the statement is between begin and end transaction, but still you will see this difference in the values.
Okay, I thought, the transaction was to, if you are writing it as a transaction, it will not be. Yeah, I'm getting confused with the isolation and the transaction, but the transaction definition was to write it atomic. I mean, the writes or the updates should get reflected atomically, right?
Right. So Uday, the transaction is actually depends on what isolation level you actually are using. So this whole scenario, what we are discussing here, is based on that. if your transaction level is read committed set in the database. So what read committed says that you cannot read any you cannot, no dirty read, no dirty write. So when you commit that, so that is here at this point, there's no more dirty write. So now you can, the value is already committed. So when you make a read request, so it will actually see that information now because that value is already committed.
Okay.
So Uday, like to add few points. So yes, we discussed that to complete a transaction, we need to have this ACID properties, right? Atomicity, isolation, concurrency, and also consistency and durability, right? So now what we're saying is a transaction needs to follow ACID properties, but if it strongly follows these ACID properties, if it strongly follows isolation, then your transactions will become slow, right? So now if your database is implementing the system in such a way that if you have started the read and now it has blocked your database to isolate it and it will not allow anyone to write or read, then your database as a system will become slow, right? So what we are saying is, so what databases these days are trying to do is they're trying to take a weak approach of providing this isolation levels so that your application can fulfill whatever the requirements of applications are if it does not need those strong isolation levels and still providing you some form of guarantees. Okay. So if your database is such that it is providing strong isolation level, then you will not see this problem. But we are saying that we have implemented such kind of a database which is not providing those strong isolation level to provide us better availability. Right? Yeah. So that's why it says, right, weak isolation level. So otherwise, if you have to follow a transaction and you have to follow ACID, then isolation should be strong, right? Like it should be isolated. So that's why we are discussing what happens if we follow these weak isolation levels. Okay, I hope, we can move forward here. So, so now we were saying that how will we implement this isolation level? So another point to add, Uday, to your point is, so sometimes we do this batch preprocessing jobs, right, where we have to read large amount of data. Now imagine if your data system is like it wants to follow ACID and it is blocked for that entire transaction of time, that you cannot read anything, you cannot write anything, then your system will become very slow, right? So that's why what we're saying is that if this is the scenario which happens a lot, where you need these backup kind of scenario, or where you need to run long running processes, long running read process, which are analytical or batch kind of processing, then what we can do is we can take a snapshot of your database. In that snapshot of the database, any reads, any writes which are going on right now will not be applied to that snapshot, so that you see a consistent view of your database and once you are completed with your read operation, then you can look at the next snapshot of the database to see what is the most updated view of your data. So one thing in my mind how we could implement such kind of a system is, so let's say you have your database which has some data, right? So imagine you have this another layer, right, on top of this data system. Your reads and writes are going through this system, right? So what we are saying is that we want to take a snapshot. We will take a snapshot of this, whatever my data piece is, whatever reads and writes will come at this point, it will be applied here, it will be stored somewhere here. Whatever writes are coming, it will not be applied to this snapshot. Once we are done with our work of the snapshot, then whatever rights were there, we can apply this to the to our existing database, right? So one way to do this thing is that you are storing the version of each of your data piece. So let's take an example. So let's say in my data, I have these values 1, 2, 3, 4, right? Different keys, different values. All of them are V1 right now, right? So all of them are V1. So this is the snapshot. Now, if someone is writing, let's say if someone is updating this value to 2 dash, right? So I will update the value to 2 dash and I will update the value to V2. If someone is updating again the value to do double dash, I will increment the version and I will update it to V3, right? So now when I want to take the consistent snapshot of this data system, I will look all the data pieces which are V1, right? So if I will look at this data with the version V1, 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 then I will see that everything is consistent at that point of time. Like whatever was the V1 version, I'm seeing all the data which was at that version. I don't know if I have not tried to explain this before, so I don't know if my explanation is going very good, but yeah. So I mean, so you keep this data system as a multi-version concurrency control where you are maintaining multiple versions of your data, and then and that helps you get the consistent snapshot of the system. So yeah, so I don't know, let's take some scenario. So let's say this 3 was also modified to 3 dash. So we will store it as V2. And now this transaction got completed. So how will I take a snapshot of 1, 2, 3 dash 4, 5? I don't know. Does anyone understand this thing fully? How the versioning is taken over here?
There was an example in the book, right? Like for the same problem, they explained like how the same objects will be implemented in the database.
Yeah, let's take that example. That's a good point. Okay. So this was the example, right?
Yes, yes, yes.
Okay, so now let's go through this example. So so there are 2 accounts here, right? It's the same problem. Okay, so the 2 accounts, the balance was initially 500, right? And what is this created by 3 and created by 5?
So basically they are saying in this snapshot isolation how it will be implemented, like as you explained, each version we will maintain that which transaction created this this object, like this account 1, which object created this. So let's say the transaction 3 created this account 1 in the DB.
Mhm.
And deleted by this deleted by tells us like which transaction deleted this object.
A small correction here. So the ID is the transaction ID actually.
Yes, yes, yes.
Yeah.
Oh, ID is the transaction ID. Then what is created by?
Maybe user.
Okay, some user. Okay. Okay, so the transaction ID is 1 and transaction ID is 2. So 2 different transactions have created this account. Then, yeah, Neha, you can go ahead. What were you saying?
Yeah. Basically, like they are saying like for each object in DB, they will have these 3 attributes, like which transaction created this object, which transaction deleted this object, and what is the balance like what is the value of that object. So basically like we will determine that this object is created by which transaction and deleted by this by which transaction by using these identifiers. So initially like they're saying that account 1 and account 2 was initially created by transaction 3 and account 2 was initially created by transaction 5. And there is no deleted by, and this ID is just identifier of these objects. And then and when we update and whenever we will update, we will not change this original object. We will create another version of this object where we will mention that which transaction now, like we have an update, right, like 500 to 600. So now this object value will be 600. So we are saying that this transaction 13, which is this update, which is the transfer object, transfer request, right? So there we are saying like here, this version is created by 13th transaction, deleted by null, and ID is this ID and the balance value is 600. And we will also update the previous version, saying that this previous version we will delete. So this we are saying that
right, it was deleted by 13 transaction. Okay.
Okay, and and they're saying like we will not delete this previous object. We will create another object where we will identify like this new value is created by which transaction. So later on, so this is kind of a snapshot. Like this previous version is basically telling us the snapshot of that particular object.
Right. Yeah, okay, got it. And then here, so here also the initial value was this, right? So the new value is created by 13th transaction. So ID is like key. So ID is key value pair, right? So this key is 1 and value is 500. Key is 2, ID is 500. So key will remain same. And the value has now changed to 500. And this object was created by 13th transaction. And so it will make this one as deleted because according to 13th transaction, this object is no longer valid. So that's why it's deleted by 13, right? So now when I have to read bank accounts with ID 1, I will pick one. How will I pick the objects here? That I have to pick this first object out of the two objects.
I think there were some rules which were defined that the transaction will not read anything which is not committed or aborted. And second rule is the transaction will not read anything which is written by a transaction higher in number. So let's say this update was done by 13th transaction and this transaction ID is 12. So 12 will not read anything above 12. So so 12 transaction will still read 500. Even if the update is done, it will still read the value 500.
Oh, yeah, nice. Okay, so this
there are two rules to create these snapshots. So when actually transaction starts, so it actually does not include any transaction which is still running. So it does not include that in the snapshot. It only includes the transaction which are already committed.
Right. Yeah.
And the second, it also not include the record which are marked as a deleted.
Yeah. So basically, so when this transaction started, I think this transaction was given ID 12 because this transaction started after this transaction 12. So that's why it is given a ID which is more, which is 13, right? So now when this transaction will start reading the data, it can only read the data which is before or equal to 12, right? So that's why it can read this value because it was created by 3. 3 is less than 12, right?
So
and then
small correction here. So there may be possible that it may not include any transaction which is smaller than 12 if that transaction is not committed yet.
Yeah, if it is not committed, yeah, right. No, but if it is not committed, okay, then it will have the transaction ID more than that, right? If it is not yet committed, because it happened after 12. Oh, it might. Oh, yeah. No, it might be happening before 12. It started before 12,
Yes.
but it is still not completed, so it will not pick that also. Okay. Yeah. Right.
Yeah.
So anything which is less and it should be committed. So this is committed and this is less 3. So it will take this value here. Now, when it is trying to read these two objects, he has option of 2 objects, 5 or 13. Both of them are committed. So it will take 5 because 13 is more than 12, right? So it will pick this object. And so that's how it will get the consistent snapshot of the data. Yeah. Okay, so this was the consistent snapshot. I have not read anything after this actually. So has anyone gone through the book after this? Snapshot isolation.
Can you share the notes?
The notes, yeah. Okay. Yeah. So we have discussed this. Snapshot isolation is a boon for long-running read-only queries such as backup and analytics. Like read committed isolation, implementation of snapshot isolation typically use write logs to prevent dirty writes. Yeah, so when we have to implement write, we have to take the write logs. Write can block the progress of another transaction that writes to the same object. However, read do not require any logs. Right. So in this system, when we were writing, right, so we will be taking logs because we don't, so we will be taking those row level logs. So for this ID, no one else can write. But for read, we don't need to take any logs. So in fact, our write logs will not block the read, right? And for read, we don't need to take any logs, right? And for write also, the logs which we are taking are only to block another write. We don't need to block any reads, right? So this is what he's saying, that for reads, we do not need any logs, and write can only block the process of another transaction that writes, right? So from a performance point of view, a key principle of snapshot isolation is reader never blocks write and writer never blocks read, right? And I think we can also say that readers never block reads, right? Read are not blocked. Because it maintains several versions of an object side by side, this technique is known as multi-version concurrency control. So these were the visibility rules. When a transaction reads from the database, transaction IDs are used to decide which object it can see and which are visible. An object is visible if both of the following conditions are true. At the time when reader's transaction started, the transaction that created the object has already committed, right? Which is the first point which Praveen was saying, that it should be already committed. The object is not marked for deletion, or if it is, the transaction that requested deletion has not yet committed at the time when the reader started, when the reader's transaction started. Okay, the time. So both of these are related to committed, right? That this also says that the transaction should be committed, and this is also saying that the transaction should be committed.
Whenever, I mean, even if the object is updated or deleted, you don't write into that object, you write it as a new value, I guess.
Yeah. No, yeah, that's right. You are all.
So you don't require writes for the new, you don't require locks for the writes as well, right? Since you are writing as a new object.
Okay. That's a good. No. Yeah. Let's think about it. Okay, this is a good point. So you're saying that since I'm writing a new object, why do I need write locks, right?
Yeah.
Right, Uday, this is your question. Okay. Uh, so the problem that I see is that so let's say my initial object is this, right? If two processes are trying to write at the same time, and I don't provide the isolation at the write level, then they might update the incomplete values of the data. So in this case, because there is single value, it is harder to explain. But let's say my key was 1, and I had, for this key, I had 2 values, right? That the balance and some other value. Now let's say my one write has updated this balance, but it has not updated that other field. And the second transaction now sees this data and it tries to update that data. So it will become inconsistent at that point. Right? So that's why write needs to be blocked. So let's take a simple example of one value. So ID is 1, right? And the value is 500, right? So now let's say first write comes, and first write it increments the value to 500 plus 100. So it increments the value. It is storing in it is in counter, and it is going to make it 600. But before this value was committed, another write came, and it also wants to increment to 100, right? So overall, someone has added $100 and $100 to my account, so total balance should be $700, right? But let's say if I'm not blocking write, this write was not completed, and someone else will also now see this value 500, right? Because this is the last, this was still not committed. So it will also increment it to 100. It will then say that the value is 600. Both will commit the value as 600. So I have lost $100 in that case.
I think you are talking about serializable. In snapshot, the snapshot can suffer from, the concurrent writes. Yeah.
So that's what we are saying, that if concurrent writes, whenever two writes are happening concurrently, they have to be isolated. They should be atomically happening. So this is what we are saying above, right? That we were saying that write can block the process of another transaction that writes to the same object. So your point was that why do we need write locks, right?
Yeah, so actually, so Uday, these snapshot, the snapshot version what a database create is for only for reading. It's not for writing. The writing will happen with the actual object, not with the snapshot object. So that's why we need the lock on that.
So how write will happen on the actual object? So write will happen looking at the latest value, right? So
Right.
this will pick the latest value, and the write will happen on top of it. But
One doubt. So I'm guessing that let's take account 1 itself, and there's a let's take the transaction ID 3 is also trying to update account 1 itself. Now both are trying to update the account balances by 100. Let's say they're trying to. Yeah. Now since you are updating, they both want to delete that row.
Right.
Since update is nothing but a delete of the old row and writing of a new row, you will need to delete that old row and write a new row. So the new row I understood, because you are writing with a distinct its own transaction ID that will not mess with the other transactions. But what will happen? Who will be marked as deleted by the other so since both are trying to update by that value, who will be marked as deleted by in that that row?
Oh, yeah. So, yeah. So,
I believe in that case, there will be a lock. Only one transaction will be able to mark that row deleted.
yeah. So, so that's why we're saying that we need to take write logs. So if two transactions are trying to do, so one which will acquire the log first, right? That will be allowed to modify it. So it will modify it to 600. Now the second transaction will be in the queue. So now when the lock is released, it will see this as the value, and then it will modify this. So now it will add $100 to 600, and it will modify this one. So we will have 700 as the total balance, right?
No, I don't think so, because the transaction is still in progress. It has not completed. So, it may happen that after the next SQL statement is updated, the integrity might be wrong, and it can get aborted as well. So that deletion should not be visible to the other transaction. So if we let's take the transaction one itself, the 12 itself holds the lock, and it has written that deleted by equal to 12. Since the transaction has not completed, if you write it to that row itself, it will that might get aborted, and we have written an inconsistent data.
Okay. So you are saying that these two ads, like $100 additions, was part of the same transaction. Are you saying that? Or were they different transactions that happened concurrently?
So 12 and 3 are happening on account 1 itself. Both are trying to increment the balance by 100. Let's say 100 itself.
And they are different transactions, or are this like it is the same transaction?
Both different transactions.
So then what's the problem? So then how will you create inconsistent data? Because so you have started two transactions, right, which are trying to increment. So any transaction which acquires the lock first, it will increment it, and it will commit this value 600, right? Now the other transaction will see this, and it will update it here like this, created by, so whatever was your another transaction, let's say it was 14, and then it will mark this one as deleted by 14, and it will create the balance as 700. So isn't it right? How did we create inconsistent data at any point in this system?
I don't think so. I mean, Abhishek, here it will another transaction will be able to update it to 700 until the first transaction commit it and release that.
Yeah. That's what I'm saying. First transaction has to complete and commit and release the lock, and then second transaction will.
Yes.
Can I make a small note here? I'm not sure snapshot isolation makes use of locks to handling writes. As far as I'm aware of, when you have a transaction that's going to write data, it also operates on a snapshot of the data. And at the commit moment, the transaction manager verifies if the data you are committing, if your snapshot has changed. And if it detects that a change has occurred, it aborts the transaction. Otherwise, then it commits. So what I'm saying is maybe locks might be used when you have snapshot isolation, but the way some databases are implementing it is by not relying on locks, but relying on snapshots taken at the beginning of the transaction, even when writing data.
They don't take logs, and then what did you say? So I know
they take a snapshot. So you have a transaction 13.
Right.
The database takes a snapshot of the data and provides that snapshot to that transaction. transaction do these two updates on the snapshot. And when you call commit, the transaction manager verifies if the data has changed by some other transaction.
Yeah. Okay, got it. Yeah, okay, yeah. So I agree. So there are two ways to do this thing. So one is taking the logs, which is called pessimistic locking. Another is optimistic locking, which is compare and set. So compare and set is that so let's say my initial data was this, right? And two transactions are trying to modify it, 13 and 14. They're trying to increment it by 100. So what we are saying is that both will be given this value, 500, and both will try to update the value. And then one of them will come first, one of them will update the value to 600. When the second one will come, it will see that the object has changed. I was trying to modify 500, but the object has now become 600. So that other transaction will get failed because it is modifying an object which has changed meanwhile. So it has to retry, right? So that is compare and set that you're talking about. Yeah.
Yeah, but in the book they have mentioned that snapshot isolation for write, they use write locks. At least by the book, that's the definition. Like,
okay, so they don't use compare and set for snapshot isolation. Is that what you're saying?
Yes. For writes, they use write locks to
Okay.
prevent writes.
And did they mention the reason? What's the reason?
No reason. Like that's just like the algorithm they mentioned. Like readers will read from the snapshot. Like readers will not block any reads. But for write, to prevent dirty writes, they will still take write locks.
Mm-hmm. Okay, yeah. Okay, should we move on? Let's see. So we were here, an object is visible if both of the following conditions are true at the time when reader's transaction started. The transaction that created the object has already committed. I did not understand these. Both of the points are talking about that the transaction should be committed. So this also says it will.
Second is not clear to me.
Yeah, the object is not marked for deletion, or if it is, the transaction that requested deletion and had not yet committed at the time when reader's transaction started.
Yeah, this is what I was talking about. So if the transaction is not completed, we cannot update the deleted by, because at a later point of time, the transaction can get aborted.
Yeah, that's true. Yeah, you're right. So transaction has to complete. If it is not completed, we will not commit. I mean, when we have committed the data, then our transaction gets completed, right? This is what you are saying, right? Or are you saying something?
Yeah, so only when a transaction completes, only it can the row can get updated.
Mm-hmm. Yeah. So yeah, that's true. Yeah. Okay. By never updating value in place, but instead creating a new version every time a value is changed, the database can provide a consistent snapshot while incurring only a small overhead, right? So yeah, this we have already seen. Index and snapshot isolation. Append only copy on write variant that does not overwrite pages of the tree.
So I actually figured, I think it's related something to update the B-tree index. I saw that in the chapter 3, they were talking about that copy on update.
Okay, yeah. So basically, yeah, so this point is that whenever you have to write some data, right? You have some piece of data, you want to write it. So you have two options. One option is that you modify this object in place, like you are modifying this object. The problem with that is if you're doing that, then you also have to block reads, because while this data is being modified, it might be in some inconsistent state. So unless your write gets completed or committed, you have to acquire read locks as well, right? Another approach is that you take this object and you create a copy and modify the copy of this object. And when you have modified the copy, then you atomically swap these two, right? If you are doing this, then you don't need to take read locks while you are writing the data. You don't need to block reads when you're writing the data. So this is the same point being mentioned here, right? That append only or copy on write, which means when you're writing the data, either you append, you don't modify in place, or you create a copy and then write. So these don't override the pages of the tree when they are updated, but instead creates a new copy of each modified page, right? So yes, and like there is the website which explains the implementation of Git, right? Git, which does version control. So Git also does very similar thing, that it creates a copy of each of your modifications of code. So it creates that copy tree so that you can go back at any point and you can see the version. So this version control, you can see that how Git can make use of this. So if you have all the versions stored of your data, right? Then at any point of time, if you want to see how did my data look at if I'm looking at this version, I can see and get those values, right? One another interesting thing, I think if someone has read, he talked about this tree, how they actually modify the tree. So let's say if my B tree was something like this, right? And if I have to modify this node, right? So what you do is that you take this parent, you take its parent, and you create a modified object, and that you are going to replace and append, right? So basically the point is, if you want to update this, probably the reference to this might also change, because your parent, it might have to split or it might have to do something. So this reference might change. So you have to keep the value of this parent as well. And then again, this might have also changed because the B tree might split. So you have to keep reference to this parent also. So like this, you keep a new copy, which is another version of this tree, and you only keep this parent. You can reuse this data because this is not changing. And that's how you can, so like this will be V1, this will be V2, and that's how you can, so whenever you want to get V2 version, you can apply this tree to this original data and you can always get V2, right? And similarly, if you want to get V3, like if you want to modify something else, you will apply these changes and then modify it.
That would be, I mean, if you're having the whole, that would be whole lot of data, right? I mean, I read it as a different one. So you just only maintain that page itself as a snapshot. So
you're saying only this has the snapshot?
Yeah, so the parent has just the reference just has to get updated. The parent has to point to a new page, but this page, I mean, only the modified page will be written as a copy on write or something. If you take the whole snapshot of the tree, it would be, I mean,
not the entire tree. It's parent, because so you are saying, right? So now I have a new page, right? This was my original page, and this is my new page. So this data has also changed. So first I was saying that pointed to P1. Now I'm saying pointed to P2, right? So by snapshot, what I'm saying is I have every piece of information which was before. I have every piece of information which is new, so that I'm not losing anything, right? So that's why now here it said that my right child is P1. Now if I'm saying my right child is P2, this data has changed, right? So that's why you need to create and keep the new copy of this also, so that it knows that this has changed. Let me see where I read this in book. Do you agree, Uday?
I'm seeing, I mean, in this way, you need to store the whole tree, but
Not whole tree,
Not
it's
whole
parents.
tree.
It's
So-
all its parents.
Yeah, so every write actually create a, so book says that every write create a new root. So the page which are not changed, so you keep as it is, and the page which are changed, you just change the reference in that.
okay, got it.
So let me bring that snapshot. So it says this, right? Although they also use B trees, they use an append only copy on write variant that does not overwrite pages, right? So we are not overwriting. We will create a new copy of the tree when they're updated, but instead creates a new copy of each modified page. Parent pages up to the root of the tree are copied and updated to point to the new version of the child pages, right? Any pages that are not affected by a write do not need to be copied and remain immutable. Okay, so
this is why, I mean, in the last chapter or something, we have read that LSMs have a less right. I couldn't remember that name. Less rights when compared to B trees or something, maybe.
or write amplification, right?
Yeah, right amplification.
So we were saying LSM trees has less write amplification compared to B trees. Okay, so you're saying that because you have to update these parents and all, so each write is like leads to multiple object writes. So that's why this B trees have a lot more write amplification, right?
Yeah, I'm guessing so.
Yeah. Okay. Okay, so this is good. So this was interesting. What else? So repeatable read and naming confusion. Many databases that implement it call by different name. In Oracle, it is called serializable, and in Postgres in MySQL, it is called repeatable read. It defines repeatable read, which looks superficially similar to snapshot isolation. As a result, nobody really knows what repeatable read means. Okay. So yeah, I don't know if this is very relevant. We can probably skip this part unless someone is interested.
This is just author is just trying to explain that. I mean, each database has their own name for snapshot isolation. So like Oracle call it serializable.
Okay, so let's go to this preventing lost updates. There are several. Someone was saying something.
Time check, already 8:45, so not sure.
So okay, so do we want to wrap up? I think we can cover this part. Let's. Is it big? I don't know. Preventing lost updates.
Yeah, I mean it's a big topic. So
okay.
There are multiple. So here,
I think we have talked about this locking mechanisms.
Talked about
So
we can go through that. I mean, not
let's see how much we can cover in 10 minutes, and then we can probably repeat it next time if we are not able to complete it. There are several other interesting kind of conflict that can occur between concurrently writing transaction. The best known of this is lost update, right? And it is what we have discussed before, that if two transaction was concurrently modifying, so we will still see 600. So we will see that one of the transaction has lost its value, right? So the lost update problem can occur if an application reads some value from the database, modifies it, and writes back the modified value, a read, modify, write cycle. If two transactions do this concurrently, one of the modification can be lost because the second write does not include first modification, right? We have already discussed this. So incrementing a counter or updating an account balance, making a local change to the complex value, two users editing wiki page at the same time, right? So these are some examples. So atomic write. So many databases provide atomic update operation, which remove the need to implement read, modify, write cycle. Not all writes can easily be expressed in terms of atomic operation. For example, updates to a wiki page involve arbitrary text editing. So basically to this point, right, what we are saying is if we are using the second approach, which is compare and set. So for compare and set, you have to first read the value, what is the read value, and then you modify it, right? Or if you are taking those explicit locks, then you don't need to read the value, then you can just acquire the lock. So that's when many databases provide atomic update operation, which removes the need to implement read, modify, write cycle in the application code. So in that case, we don't need to read the value. But then it is saying that not all writes can easily be expressed in terms of atomic operation. For example, updates to wiki page involve arbitrary text editing. I did not understand this thing.
The page editing might be the concurrent editor, the Google Sheet, something like that. You cannot transport the single page update. You cannot post the complete page again, right? You can just only say the user has edited this, so that has to be transformed in a different operation because multiple users are writing it to that page, right? The operational transformation that we have discussed here.
The operation transformation we have discussed, that's right, but it can be expressed atomically, right? So the operation transformation we wanted to do, if we want to support like this kind of multi-leader kind of approach where we are saying everyone can modify the page and we will allow everyone and we will eventually merge your data. But I'm saying if we want, we can also express that atomically, that this is the snapshot of the page, you modify it, and now you can update that entire page atomically. And if someone else has modified the page meanwhile, they will be returned as failed because they are modifying the page which is already modified. But probably okay.
Yeah, by the time the response came, the user might have closed the tab or some. Those things also can happen.
Okay.
So it might be a different. It might be somewhat harder to implement it like that.
Okay. Cursor stability. Atomic operations are usually implemented by taking an exclusive lock of the object when it is read so that no other transaction can read it until the update has been applied. Another operation is to simplify force. Another option is to simply force all atomic operation to be executed on a single thread. Okay. So one is locking. That is fine. Another option is to force. Okay. Yeah. If we don't allow multiple threads, if we have just single thread, then also we will not have this problem of concurrency. Yeah. Here they're saying that don't have concurrency at all, right? You are just having a single thread. So explicit locking. If the database built-in atomic operation don't provide necessary functionality, it is for the application to explicitly lock objects that are going to be updated. Example, the for update clause indicates that the database should take a lock on all rows returned by this query. Okay. Atomically detecting lost updates. An alternate is to allow them to execute in parallel if the transaction manager detects a lost update about the transaction and force it to retry it, right? Which is what we have discussed. So this is read, modify, write, or compare and set. I think read, modify, write, and compare and set are the same thing, isn't it? Aren't the same? If database that don't provide transaction, you sometimes find an atomic compare and set. Avoid lost updates by allowing an update to happen only if the value has not changed since you last read it. So
looks to me same. In that automatically detection is implemented by database, and this compare and set is actually you do something you set in your query statement.
okay, I think so yeah, one might be what database is doing and another is you application as an application have to do it.
Yeah.
Okay, right. Yeah, that's true. Yeah. Okay.
Because book says that MySQL does not provide a snapshot isolation for automatically detection lost update.
Okay. Conflict resolution and replication. Locks and compare and set operations assume that there is a single up-to-date copy of the data. Thus, techniques based on locks or compare or set do not apply in this context. Allow concurrent writes to create several conflicting versions of the value and to use application code or special data structure to resolve and merge these versions after the fact. Yeah, okay. So this also we have discussed. So here in our one of the previous session, so one approach we are saying is that you take the lock and modify it, right? So another thing which happens in multi-leader kind of approaches where you don't have a single copy of the data is multiple threads can modify the data and they will keep, so the database will keep both the version of the modified data, and then it's up to the application logic that how it should merge the two modified values of the same data, right? The last write wins conflict resolution method is prone to lost update, and unfortunately last write win is the default in many. Yeah, the other approaches that you don't take lock, you don't do anything, and you just let last write win, which will lead to lost data, but in scenarios where it is okay, like a lot of databases, I think by default provide this approach, right? So any question up till here? Any question in any of these 3 points? Or any some more insights? I think we can wrap up at this. This is, I think, a different topic, right? Skew. Yeah, this is a different topic. Let's wrap up at this point. Okay, yeah, so let's wrap up. I'm sorry I was not prepared for this session. So yeah, it was I think not so great, but yeah, at least we all read it together and learned something. Let's stop the record.
MySQL and PostgreSQL, they also have snapshot isolation in read committed. It's interesting to note that. But the snapshot isolation in read committed works differently from repeatable reads. If you do the same select two times inside the same transaction in read committed, you get different values because the snapshot is recreated inside the same transaction. So be aware of that, because when we read the documentation from MySQL Postgre, we are going to see snapshot isolation, and we might assume that it also takes care of a non-repeatable reads, but it does not.
Okay.
In repeatable read, the snapshot is taken at the beginning of the transaction, and it's maintained this way for the entire duration of the transaction. So you don't get these problems that you are going to observe in read committed.
So you will get this problem in read committed, right? If
yeah, because the snapshot can be recreated in the middle of a transaction.
Right.
If you do the select twice, for example, 2 times inside the same transaction, the second select is going to get a new snapshot.
So
Okay.
that problem, Alex, you're talking about the read commit transaction level, right?
Yeah, that's right.
Yeah, so I believe that that was the problem we were talking. So the Neha was having a confusion about that. So when second, Abhishek, could you please bring that?
Yeah, no, I was talking about serializable snapshot isolation, which is a strong format of snapshot isolation. So I was talking about a particular implementation that's not quite, so it was a little bit confusing.
Okay, I have not read up to that. So
yeah, I have also not read up to that.
Yeah. But snapshot isolation is that what was discussed. I was just moving too far ahead without. About that last right wings conflict resolution that we saw here, there's an interesting aspect about Cassandra, because Cassandra implements this sort of conflict resolution. And Kleppmann mentions that last right wings can lead to lost updates. And I think he's talking about Cassandra specifically, because in order to determine what right is going to win when you have conflict or multiple rights, you need to have some sort of a timestamp to determine that. And if you read the original Dynamo paper from Amazon, Dynamo relies on vector clocks or version vectors. So they are monotonically increasing numbers used to determine which write happened before or later. And you don't see lost updates in Dynamo. But in Cassandra, the timestamp is based on wall clocks. So now you can imagine, if you don't have fully synchronized clocks between all the Cassandra nodes, then you might observe some of your updates being lost when a replica tries to deal with all the versions that were concurrently created by a same cell or a same row.